Hello everyone, we are going to discuss question number 56 from MTP4. Here we have to find out the biological standard potential for the conversion at 25 degrees Celsius, and it's given that the pH value is 7. Reduction half cell reaction is also given to us, and A naught value is given as minus 0.11 volt. Now we will apply the Nernst equation for the half cell reaction. So it will go as E equal to E naught minus RT by NF. Here N will be equal to 2. There are 2 electrons transferred. ln of activity of NADH divided by activity of H plus into activity of NAD plus. Now we know that it's in standard state, so the activities of NADH as well as activity of NAD plus will be equal to unity. Substituting these values, we will get E equal to E naught plus RT by 2F ln of activity of H plus. Now, solving it a little further, we can substitute the term negative of log activity of H plus as pH, and that will come out to be E naught minus 0 to 9.58 into pH. So, substituting the value of pH now and the value of E naught, we will get the biological standard potential at this pH value as minus 0.32 volt. Hello everyone, we are going to discuss question number 57 from MTP4. Here it's given that a dye absorbs light of this wavelength, and then light of another wavelength is emitted, and also provided that 47% of the absorbed energy is re-emitted as fluorescence. So we have to calculate the ratio of quanta that are being emitted to the ratio to the number of quanta that are being absorbed. Suppose energy of light absorbed in one photon will be hc divided by lambda absorbed. So total energy that is absorbed will be equal to number of photons multiplied by energy absorbed by one photon. So that will come out to be n1 hc by lambda absorbed. Now energy of the light that is re-emitted in one photon will be hc by lambda emitted. So the energy that is being re-emitted, total energy will be equal to n2 into hc by lambda emitted. Now we will go in the accordance with the problem, that is total energy emitted is equal to 47% of absorbed energy. So substituting the values, we will get E re-emitted equal to 47 by 100 into E absorbed. So substituting the value of E absorbed and the value of E emitted, we will get n2 divided by n1 equal to 47 divided by 100 into lambda emitted by lambda absorbed. So the final ratio of n2 divided by n1 will come out to be 0.527. Hello everyone, we are going to discuss question number 58 from MTP4. Here it's given that the equation of state for a gaseous sample is given by PVM equal to RT into 1 plus BP. It undergoes Joule-Thomson expansion from 100 atm to 1 atm. Cp is also given to us, that is 5R by 2. Here Joule-Thomson coefficient is given as 0.21, and the value of constant B is also given to us. We have to find out the entropy change for the gas. We know that entropy is a function of temperature and pressure. So entropy change will be given as del S divided by del T at constant pressure into dt plus del S by del P at constant temperature into dP. We know that del S by del T is given as Cp upon T, and we also know the relation between del S and del V, that is del S upon del P at constant temperature is given as negative of del V upon del T at constant pressure. So that is a thermodynamic relation between these two at constant temperature and constant pressure respectively. we are given the value of Vm, that is RT by P1 plus Bp. So we can calculate the value of del V upon del T. That will come out to be RT upon P into 1 plus Bp. So R into 1 plus Bp divided by P. So now we will substitute the value of del S by del T and then del V by del T in the previous equation. Substituting these values, we will get dsm as Cp divided by T into dt minus R by P into 1 plus Bp dP. We can separate the last two terms in order to integrate, and after that we will integrate the whole term. As the variables are temperature and pressure, so the range of temperature will go from 352 to 373, and the pressure will go from 100 atm to 1 atm. Substituting the limits, that are lower limits and upper limits, we will get the entropy change as 35.9 joule per Kelvin per mole.